Good afternoon 9.7. This is your Do Now activity for today's lesson on power. So if you pause the video whilst you have a think about these.
Okay, so some of these units you might have been familiar from before. So things such as millimeters and centimeters we use in our everyday lives, particularly at school. Kilometers, again, another distance that you're probably familiar with from everyday lives. We're a bit weird in this country. We have two different units for distance. We've got our kilometers, which is what we call our metric units, but we also have miles, which is what we call imperial units. And the imperial units are the historic old-fashioned units, but we still have them kept in our day-to-day society, whereas kilometers is our metric system, which typically used a lot more commonly because its numbers are much easier to work with because they are in powers of 10. Similarly, extension, thinking about what other measurements you might have come across prefixes with. So milliliters, you might have used for measuring volumes. Micrometers here, you might have, or you should have used that when you were looking at your microscopes topic in biology. Nanometers we talked about when we talked about how big an atom is. But megameter, terameter, and gigameter, these are the ones I'm not expecting you to be familiar with in terms of the meter units. However, you're more likely to be familiar with them from the bytes unit. So gigabyte, terabyte, megabyte. So files, digital file sizes, they use these units. So mega, then giga, then tera being your largest. So tera tends to be like your hard drive file size, whereas megabyte, this is more used for, say, a Word document. That file size will be in the megabytes. Gigabyte is more like the file size of an application, such as Microsoft Teams. And then terabyte is typically the amount that your entire computer could hold. So these are how those unit prefixes can be written. So this is standard form, which you may or may not be familiar with from maths. If you're not, I'm sure you will get there at some point in your maths curriculum. But when we look at these numbers, they're just telling us the number of places we've shifted our number. So for example, 1 kilometer is 1,000 meters. Now that conversion, I think we're quite happy with. But what you can see is what we've done is we've shifted that 1. So from 1 kilometer, that's been shifted 3 places to the left. So that's what that K, if we were trying to convert from kilometers to our normal, like standalone without the prefix. So prefix is just these letters before the meters. That's what we'd have to do here. So that 3 is effectively a +3. So we're moving it 3 places to the left. Whereas with our minuses, we're going to be moving it 3 places downwards. So if we want to convert from 1 millimeter to a meter, we're going to be needing to move it 3 places downwards. So 1, 2, 3. So we're going to be having a few zeros. So 1, 2, 3 decimal places, we've moved it down. So remembering where that point is, we're then moving it 3 places down from there. I don't know why I did a 3 there. It should be a 1, sorry. So it doesn't change number, it just changes the position.
So I'd now like you to consider this question. What do you think power means? Where might you have heard this word before? So pause the video whilst you have a think about this.
So whenever we talk about power, we're looking at the rate at which energy is transferred. So a powerful car is able to go faster because it's transferring that energy to kinetic energy a lot quicker. So the way in which we can write this, whenever we're talking about rate, we're always talking about something per second, just like you would have done with your other teacher. So when you're looking at speed and velocity, so that is the rate of change of distance or displacement, the rate of change at which an object has moved. We're familiar with speed being in meters per second. So that's because it's the rate of distance that's covered. So whenever we deal with rates at all in science, we're always talking about something per second. So the way in which we calculate power is through this equation here. So power is the amount of energy transferred per the amount of time it takes for that energy to be transferred. So pay close attention here to our units. So energy being in joules and time being in seconds. You might see it written in symbol form, and this is probably the form that I will use when we're doing worked examples, just because it's a shorter-hand version. But this is the unit which we measure power in. So we don't actually measure power in joules per second. We could, but we don't. They are equivalent units though. So 1 joule per second is equivalent to 1 watt. So 1 watt is 1 joule transferred every second. So those units are equivalent. We use a capital W though because it's named after a scientist. So the scientist Watt was given this name of the unit of power, which is equivalent to joules per second. So 2 things which I'd like you to write down is this definition of what power is, and then also this equation, including those units that we've just specified. I think it might also be helpful for you to know that 1 watt is equal to 1 joule per second, just to reinforce that idea of what units we are using for this.
So pause the video while you jot these down.
So we can also talk about it being work done. So we've talked about when we lift things, we're having to do work in order to do that. But work done is exactly the same as just the amount of energy being transferred against a force. And you'll look more at work done in other lessons. So out of these appliances, which do you think is the most powerful?
So again, pause the video whilst you have a think about these.
Okay, so these are the answers.
So did any of these surprise you? I think the fridge is normally one that surprises people because it's quite a low power rating compared to some of our other kitchen appliances. So the reason for that is it has a lot of insulation, and so actually not a lot of energy needs to be transferred over a period of time. By opening and closing the fridge, however, we then require the fridge to do more work to retain that lower temperature.
We are going to look at how we're going to do our power calculations. So for those of you who are unfamiliar with how I like workings laid out, we use this principle here, using less to make sure that we're showing all the workings that we need. So the L stands for list, the E for equation, S for substitute, and S for state. So with our list, this is our variables, but also doing any conversions of our units that we need in order for it to go into that equation that we've written down. And then when we are stating our answer, we must include our units in our answer. So to start with, reading the question, so looking at what variables I have. So how much energy, this is our unknown that we're trying to find out. So our energy transferred is our question mark. And then we've got a power here. So P equals 800 watts. And then our T is 10 seconds. Now notice seconds and watts, these are our units that we like. Energy, we like in joules. Some questions, they might give it to you in hours or minutes, and we'll need to convert those into seconds. Our equation is the one we wrote down earlier. So P is our rate of energy transfer, but we can rearrange that to find E. So in maths, whenever we want to get something onto the other side, we need to do the inverse operation. So we need to get T onto the other side to leave E by itself. At the moment, T is being divided, and therefore to get it onto the other side, we're going to need times. So if we times both sides by T, those T's then cancel because E times T divided by T, they cancel out. And so what we're left with is E equals P times T. So that's our equation for what we're using. We can then substitute in our values. So E equals 800 times 10. And then our final answer is going to be 8,000 joules. So stating my units there, they might have asked for it in kilojoules. So to do that, we divide by 1,000, just like how we would do for meters and kilometers. So that's the first example for us. So what we've now got is an example for us to do together. So what are my variables going to be? So if we type them in the chat, what is our variables from this question? So out of power, energy transferred, time, what variables have we got? Are we having to do any unit conversions? So our power is 2.1 watts. And again, we're after how much energy, so E is question mark. What is our time? 30 minutes. Do we like it in minutes though for this equation? To convert it to seconds. So this is our time, but because it's in minutes rather than seconds, we're going to need to convert. So 1 minute is 60 seconds. So to do 30 minutes, we're going to have to do 30 times 60, which is 1,800. And then our equation is the same as we just had. So we looked at rearranging that that P is E over T. So in order to get it in terms of E, we said we need times by time on both sides to remove it from the side of the equation with the energy transfer. Substituting in our values, how we're going to work out what E is, what numbers are we substituting into that equation? E equals P times T. So power 2.1 times our time of 1,800, and then finally stating our answer, 2.1 times 1,800 comes out to be 3,780, and remembering to include my final units of joules. So that's the remainder of the work for this lesson, but I just want to talk you through how to do the homework as well before I let you crack on with it independently. So there's a worksheet carrying on calculations with this. The start of the worksheet is doing some unit conversions, but I don't want you to worry too much about those if you haven't done those in maths. If you understand it and can do it, that's absolutely fine, but it's not our main focus of this lesson. So with the homework, we're looking at how we can actually calculate how much the energy that we're using is costing us. So here you'll notice we're using a different unit. So instead of watts, we're looking at our kilowatt hours for our energy used and kilowatts for our power. and our time being measured in hours. But this is no longer joules. This is kilowatt hours as our amount of energy that we've used. So that might be a phrase that you've heard before. If you've ever seen like a smart meter, it's probably measured using kilowatt hours. The cost per unit, so kilowatt hour being a unit, varies depending on what energy company you're with. So in your homework, these are the sorts of questions that you're going to be asked. So I just want to go through this example together so that we're happy with how to do those. So we've left a 3 kilowatt heater on. So this is our power in kilowatts. You put it on at 8 AM and leave it until 4 PM. So this is 8 hours. So now, because we're using kilowatt hours, we can use our time as hours. So this allows us to calculate our number of units. So by doing our power, which is 3 kilowatts, times 8 hours, so 24 kilowatt hours. If we have 1 kilowatt hour costing 12.5p, how much would it cost to leave on? So to then get our cost, we're doing our total number of units, 24, times the cost for one of those units, 12.5. So that comes out to be 300p, so it was 12.5p, but we could convert that into pounds by dividing by 100, because there's 100p to a pound.